Okay, now in the previous example, we don't really need this Marchobly-Hastings method because we know it is normal distribution, and we can always use R to generate it easily. Well, Marchobly-Hastings is really useful when we don't know the closed form of our target distribution. Now let's look at a real example in Bayesian model selection. Bayesian data analysis and statistical inference use MCMC. 18 students at a university who had failed a mathematics skills assessment test took a program designed to improve their skills. They were randomized into a treatment group where we have 10 students and a control group, 8 students. Each of the 18 students was exposed to a daily subliminal message flashed quickly on a screen, too quickly to be read, at least consciously. The message for the treatment group was, "Each day I'm getting better in math." The message for the control group was, "People are walking on the street." Each student took a pre-test before the program and a post-test after. Our job is to speculate on whether the subliminal message had an effect on the test scores. Okay, here is the data. Okay, so you see in this data we have 3 columns. The first column tells you which group it belongs to. Treatment is 1, control is 2. So those are treatment, those are control. And then for each student, we have pre-test score and the post-test score. Those are the pre-test and those are post-test score. We'll look at each person's improvement, that is the difference between the post and the subtract pre-test. We imagine that we are seeing a sample from each of 2 population distributions of improvements, a treatment population and a control population. And we can formulate our questions something like, is the treatment population mean greater than the control population mean? If so, how much? Okay, so this is actually much more like a 2-group mean, the difference in the mean problem. And we know usually we can use a t-test, right? 2-sample t-test to solve this kind of problem. Let's see, in our case, clearly the sample size is small. It's not accurate to use a t-test. And let's first read the data into R. So this is R code. Data equals to read.table. This is my file, math score. Header equals to true, and the separator is a comma. And we can look at the summary date. And improvement equals to date. The third column subtract the second column. Okay, this is the third column, this is the second column. Okay, and treatment equals to the improvement where the first column equals to 1. Control is the improvement that the first column equals to 2. And we can also draw a picture. Just look at how the data distributed. Right, we can first change the x limit between the minimum and the maximum, and then we partition the whole figure into 2 rows, 1 column. And in the first row, I will draw the histogram for treatment group. In the second row, I will draw the histogram for the control group. So you can see. This is the first treatment histogram, and this is the control program. Clearly, you just eyeballing it is not so clear whether it's the treatment is bigger, the score is bigger than the control, right? So we will try to use the Bayesian method to figure it out more. So we will use a very common type of model. We imagine 2 populations, each with its own normal distribution for the improvement variable. So here is the model for the Bayesian data analysis. Let's say for the treatment group, the improvements in the R, we actually put the data in TRT, right? Actually, they are IID comes from normal distribution with a mean equals to mu1, variance equal to sigma 1 square. Okay, they are IID from here. And for the control group, the improvements, the data actually in the vector control, their IID comes from normal, mean is mu2 and sigma 2 square. Okay, so clearly in our model, our parameter is theta, which contains 4 unknown parameters, mu1, sigma 1, mu2, sigma 2. Okay, those are parameters, and what are the data? These are the data. The vector TRT and the vector control, that's our data, right? They are IID from one normal, and this is control IID from another normal, right? So this is the Bayesian setup. We specify parameter, we specify what are the observed data, and given parameter, what's the model for the data. We call it the likelihood, remember? So in our case, the likelihood is normal, two independent normal.